Welcome friends to my YouTube channel. Now, yesterday I have finished my lectures on thermodynamics. Now, from today's lecture, I shall going to discuss the first semester honors and general topic classical mechanics. And today I shall discuss on the first chapter of classical mechanics, that is central force. Okay, central force. So the first question that arises, what is central force? Okay, you all know that a central force is always directed away or towards a fixed center, and the magnitude of this force solely depends upon the distance between the interacting bodies, or you can say the body and the origin. It only depends upon the distance between them. Okay, so this force is directed away or towards a fixed center. Okay, and magnitude only depends upon the distance between interacting bodies. Okay, if we take an example, the familiar example, we all know that the gravitational force of attraction, that we can write as minus gmm by r square into r cap. So this you can always write in this form, f of r into r cap. And since gravitational force is always attractive, there is a minus sign. So gravitational force is, okay, say this is g. Gravitational force is always a central force. The another example is that the electrostatic force, this can be written as 1 upon 4 pi epsilon naught q1 q2 by r square into r cap. So this can be written as f of r into r cap. So gravitational and electrostatic both are central forces. Okay, gravitational force is always attractive, but electrostatic force can be attractive as well as repulsive depending upon the sign of charges. Okay, so this is the definition of central force, only depends upon the distance between the interacting bodies. That's why we can write this force in this form, f of r cap, only a function of r. Okay, so this is the definition of central force. Okay, now the next question that arises, what are the basic properties of central forces? Okay, so let us discuss it. What are the basic properties of central forces? First is that it is a conservative force. It is a conservative force, and work done by this force around a closed path is 0. Okay, so how we can justify it? Say, take a closed path. Suppose we take a particle or an object of mass m from initial position to final position via this path ACB, and then returns the particle from B to A via this path BDA. Okay, fine. So this is a closed path. So what will be the amount of work done by taking the particle along the path ACB by a small distance, say dr? If you write it dwacb, that means work done due to small displacement dr, then this is this. Okay, so your f will be f of r cap and dr will be dr r cap. So this is simply f of r dr, this is simply dv. Okay, so dwacb, this is equal to dv. Okay, Okay, so this is the amount of work done in taking the particle by small distance, say dr. Now what will be the total amount of work done in taking the particle from A to B? You have to simply integrate it within the limits A to B. dV, that means VB minus VA. Okay. So this is the amount of work done in taking the particle from point A to point B. Now, if you take back the particle from B to A via the path BDA, then similarly in that particular case, if you denote the work done by this, then you take it from B to A. That means now initial final position is A and the initial position is B. So what we conclude from this, that the potential energy is only a function of R. So clearly the work done is also potential energy is a function of R. So work done only depends upon the initial and final position. So the force is conservative. You can easily conclude that the force is conservative since W depends upon V and V depends upon R. So the force is conservative. Now, if you add this, then you will get the total amount of work done in taking the particle around the closed path. Okay. If you add these two terms, then you will find the total amount of work done by around the closed path. And what is WBDA? That is VA minus VB, and this is simply VB minus VA. So this is simply 0. Okay. So we see that central force is conservative and work done by this force around a closed path is always 0. Okay. So this is the first property. Now let us discuss the second property of central force, which is this force can be expressed as the gradient of some scalar potential. This force can be expressed as the gradient of some scalar potential. This force can be expressed as the gradient of some scalar potential. How we can check it? Now we all know that potential energy is a function of position coordinates. Now since dV is a perfect differential, we can write dV as del V del x dx, del V del y dy, del V del z dz. So this line can be written in this way: I del V del x, j del V del y, k del V del z dot I dx plus j dy plus k dz. So this is simply del V dot dr. Okay. So you can express dV in terms of this, that is del V dot dr. Again, you know this relation, that gradient of potential is a measure of force. So from which you can write dV as minus F dot dr. So this is simply del V dot dr. So if you take dr common, then you can write it in this way. Okay. Now since dr is arbitrary, its coefficient will vanish. Now what you can write? You can write A plus del V is 0 since dr is arbitrary. So you can express this F equals to minus del V. So the central force can be expressed as the gradient of some scalar potential, say F equals to minus del V or minus del phi. So this is the second property. Now what is the third property? Let us check. Thus, for a central force field, for a central force field, the particle must lie in a plane. For a central force field, the particle must lie in a plane. Okay, so how we can justify it? Now we know that the angular momentum vectorially can be written in this way. Okay, taking dot product with r, so what we get? R dot r cross p. Now use this vector identity, a dot b cross c equal to b dot c cross a equal to c dot a cross b. So if you take c dot a cross b, that means b dot r cross r, this means 0. So r is perpendicular to l. R is perpendicular to L. So what does it indicate? It indicates that R is perpendicular to L. If you take L along this R and R, so this is the diagram. So the motion is confined within a plane. Okay. So the motion is confined within a plane. Okay, now there are two other properties of central force that I shall prove in my next lecture, but I can tell it. Okay, I just write those two properties that I will discuss in my second class. Okay, so the fourth property is that the angular momentum of a particle in a central force field remains constant. Angular momentum of a particle in a central force field remains constant. Fifth thing is that the total energy of a particle in a central force field remains constant, and these two I will show in my next lecture. Okay, so in our today's lecture I shall discuss the definition of central force with some examples and few properties of central force, and these two properties I will discuss in my next class. So dear guys, if you don't subscribe my channel, then kindly subscribe it to get latest videos. Okay, thank you.